Carboxylic acid derivatives are like carboxylic acids in that the carbonyl carbon is in the +3 oxidation state, but the OH group of the carboxyl has been replaced with some other heteroatomic group, which on the slide here is represented with the letter Z. And Z is typically derived from a nucleophile, like an alcohol, ROH, or an amine, RNH2, or some other nucleophile along those lines. In this unit, we're mainly going to focus on 4 classes of carboxylic acid derivatives: acyl chlorides, in which the heteroatom is chlorine, anhydrides, in which a carboxylate is actually linked to the carbonyl carbon, esters, in which an alkoxy group is linked to the carbonyl carbon, and amides, in which an amino group, or NR2 group, is linked to the carbonyl carbon. And these are definitely the 4 most practically important carboxylic acid derivatives in the organic chemistry laboratory. And they're highly analogous to important biochemical compounds as well, like thioesters and acyl phosphates, which are also carboxylic acid derivatives. So we can think of these as derived from carboxylic acids via a substitution process where Z substitutes for the hydroxyl group. And these all contain this carbonyl carbon with 3 bonds to heteroatoms, 2 in the CO double bond and 1 in the CZ bond, if you will. And of course, the most important carboxylic acid derivatives do contain the CO double bond, but we can think of any carbon in the +3 oxidation state as analogous to a carboxylic acid derivative and derivable from a carboxylic acid derivative through substitution type of chemistry. So nitriles, for example, the CN triple bond, well, that's 3 carbon-nitrogen bonds, and that's a carbon in the +3 oxidation state, analogous to a carboxylic acid derivative, and it's highly convenient to think of nitriles as such, as carboxylic acid derivatives. Oxazoles have this carbon right here, which is in the +3 oxidation state. And amidines, well, these look like amides in which the CO double bond has been replaced with a CN double bond, still a carbon in the +3 oxidation state. So each of these can be thought of as a carboxylic acid derivative, sort of in its own right, involving not just substitution of the hydroxyl group within the carboxylic acid, but also the carbonyl CO double bond. Now, one particularly important class of carboxylic acids are the amides found in proteins or polypeptides. A protein is a polyamide. It contains a backbone. It contains repeated amide groups. 2 of these are highlighted in purple in this example polypeptide here. And these amide groups are extremely important for holding proteins together. They really form the backbone of proteins in biochemical systems. The reactivity of carboxylic acid derivatives really centers on the potential of that Z group to act as a leaving group. So they're famous and practically important for their substitution chemistry at the carbonyl carbon. And in thinking about this, the mechanism is not SN1 or SN2, as we'll see. But we're still thinking of the carbonyl carbon as an electrophilic carbon. To think about the electrophilicity of the carbonyl carbon, we want to think about both the inductive and resonance effects of the group Z that's linked to the carbonyl carbon. So let's talk about inductive effects first. In a ketone or aldehyde, we've got hydrogen or carbon linked to the carbonyl carbon, and these 2 atoms are relatively not very electronegative, right? They don't pull a lot of electron density toward themselves. The story is very different with some of these carboxylic acid derivatives, particularly acyl chlorides and acid anhydrides, where the attached group is quite electronegative. That chlorine is pulling electron density towards itself in the carbon-chlorine bond, leaving this carbon very electrophilic, in fact, more electrophilic than the carbonyl carbon of an aldehyde, RCHO. And the extent of this inductive withdrawing effect, which it is a withdrawing effect for all of these atoms, right? Cl, O, O here, and N, these are all more electronegative than carbon. So to some extent, they do pull electron density towards themselves due to their electronegativity. But these atoms also have lone pairs, and this means that they can donate electron density toward the carbonyl carbon through a pi-type or resonance sort of interaction. And I want to show 2 examples of this in the space on the slide here. So the first is the amide functional group. In the amide, we have a very good electron donor in the nitrogen atom with a lone pair. That lone pair can be pushed like so to generate a resonance form with negative charge on the carbonyl oxygen, a CN pi bond and positive formal charge on the nitrogen. And this shows actually electron donation to the carbonyl carbon. So this makes that carbonyl carbon much, much less electrophilic than an aldehyde and much less electrophilic than a ketone. In fact, donation from the amide nitrogen makes the amide carbonyl carbon very, very stable. It's very difficult to add nucleophiles in at that carbonyl carbon of an amide, which our proteins are very, very thankful for since they're swimming in nucleophilic water in biochemical systems. Similar thing is going on with the ester. Here the donation is not as strong because O is more electronegative than N, but still this kind of electron flow is very important in the ester functional group, and it shows that the ester carbonyl carbon is also not as electrophilic as a ketone or aldehyde carbonyl carbon. Esters are shielded from nucleophiles to some extent as well. So this type of electron flow is relevant to all carboxylic acid derivatives. It's most important when the heteroatomic group is a good electron donating group, something like an NR2 or an OR. But even for the acid chloride, acid anhydride and the acyl chloride, we can draw resonance structures derived from this kind of electron flow. And they show us that that heteroatom has the potential to donate electron density back to the carbonyl carbon. One other thing this resonance type flow shows us is that there's double bond character in the C-Z bond, particularly when Z is nitrogen or an oxygen in an ester. This double bond character can rigidify this bond and actually make it difficult for the bond to rotate. This is very important in polypeptides, where the rigidity of this carbon-nitrogen bond prevents or limits rotation around that bond. There's an activation barrier to rotation that's actually relatively difficult to surmount. This rigidifies the amide functional group and gives some conformational stability to polypeptides.